Hi, welcome to part 2 of OWL 2 homework. So what this is going to be asking about is the idea of polar and nonpolar. So as you look at BeCl2, the best way to see it is with the Lewis dot structure. And that's why I decided to kind of go ahead and do these ones a little bit earlier. When they have a linear line, so you'll see that there's this symmetric component to them. And so the charges themselves, and what happens with electrons, or what happens with atoms, is when they're electronegative, that means they have a greater affinity for electrons, so they don't share the electrons equally. But when you see this linear kind of distribution taking place, it equalizes or cancels out that electronegative component. So even though here, when we see that both chlorines are more electronegative, because there's sort of this pull on opposite side, it balances each other out. Now, with this NOCl, what's going to end up happening is oxygen's going to have a really great affinity for electrons, and they don't have this symmetrical charge. So it's going to end up being polar. With SOCl2, same sort of idea here. There's not this symmetrical unit. Had it been SO4 or SCl4, it would have been symmetrical. But because it's not, this is going to make it considered to be polar. So I like you being able to see the Lewis dot structure next to the actual geometry of it. All right, in this circumstance here, we're going to be moving on to number 10, and this is how we classify chemical equations. So we want to talk about what kind of reaction this is going to happen. And so they are unbalanced equations, but we want to just give the idea of what kind of reaction it is. So in this guy here, the reactant is one large molecule, and through the chemical reaction, it breaks down into two. That's going to be a decomposition reaction. Versus on the flip side, with letter B, we start with two and then we make something bigger into one. That's called a combination reaction or a synthesis reaction. For letter C, we'll see that we have this iron 3 oxide plus aluminum, and that there was a swap that took place. So now we have aluminum oxide, and then we have iron on its own. Because there's this kind of single swap going on, we call it a single replacement. And then finally down below, we're going to see that there's a swap between this barium and our hydrogen here. And so because there are now two coupling pieces happening, or two doubles taking place, this is a double replacement reaction. We'll hit our button and we're good to go. All right. Question 11 is going to be dealing with energy. So we want to figure out if it is an endothermic reaction or an exothermic reaction. And we want to discuss whether or not we see the following as a product or a reactant. So CO as a gas is carbon monoxide. That's a reactant. Water is a product. Because again, we can see where the arrow is taking place and we see water on the product side. CH4 is methane gas. That's a product. And then H2 is a reactant. And it says when the reaction takes place, energy is what? Because energy is on the product side, it's going to be released. And so this is going to be an exothermic reaction. Let's try another one really quick. Okay, so we can see that we have the C2H2 on the product side. We have H2O as a gas. That's on the product side. CO2 is a reactant, and H2 is a reactant. And as you can see, energy is on the reactant side, so it's going to be absorbed. So therefore, this is an endothermic reaction. All right, question 12 is going to have us balancing equations. So it says if 3 moles of sulfuric acid react, the reaction consumes blank moles of zinc hydroxide, which would be this ZnOH quantity 2. And then the reaction produces blank moles of zinc sulfate, that's the ZnSO4, and blank moles of water, the H2O. So what we're going to do is we are going to use the idea of moles of A to moles of B to get our number going. So we're starting with 3 moles of sulfuric acid, and sulfuric acid is H2SO4. So that's our moles of A. We want to get to moles of B. So if we look at the balanced equation to get to zinc hydroxide, we have 1 mole of zinc hydroxide for 1 mole of H2SO4. H2SO4. That cancels out. So therefore, we're going to have 3 moles of zinc hydroxide. All right, for the next one, again, we're going to start with what we're given first, 3 moles H2SO4. And we're going to look at the balanced equation. For 1 mole of H2SO4, we have 1 mole of ZnSO4. So H2SO4 cancels out, and we have 3 moles. Now for water, this is going to be a little bit different, because from the balanced equation, again, we start with what we're given, 3 moles H2SO4 times 1 mole of H2SO4 over 2 moles H2O. So now we're going to double that number, and we're going to end up with 6. Submit our answer, and we're good to go. All right, same thing down here where when we try to think about going from moles to moles, we're going from moles of A to moles of B. We start with what we're given first, this 0.489 moles of bromine, which is Br2. And it wants us to figure out moles of bromine monochloride, this guy here. So again, we look at the balanced equation. 1 mole of Br2 over 2 moles BrCl. And again, it has to do with that coefficient out in front. These guys cancel out. And now we have 4.89 times 2. We get 0.978. Submit our answer, and we're good to go. All right, now for question 14, we're going with the idea of grams to moles. So this is going to be where we start with grams, and now we're going to be moving to moles. But what we have to be careful with is if you notice that our starting material isn't what we're looking for. So this is the stoichiometry problem where we're going to have to go from grams of A to moles of A to moles of B. And that's as far as it wants us to go, because it wants us to get the moles of this bromine monochloride. So we start off with 25.8 grams of bromine. And again, that's Br2. And now what we're going to do is we're going to have to find the molar mass of Br2. So we're going to go to our periodic table. Br is 79.90 times 2. Because again, we have Br2 over 1 mole Br2. The grams are going to cancel out. And now we can go from moles of A to moles of B using the balanced equation. We have 1 mole of Br2 over 2 moles BrCl. So now we're going to total this guy up. I'm going to do this. 25.8 divided by, and I'm going to put in parentheses, so that way we know what we're doing. And oh, it's not going to let me put them in parentheses. Let me get the scientific calculator out really quickly. So this makes a little bit more sense. Okay. Do a little erasing here. Okay. We have 25.8 divided by parentheses 79.9 times 2. Get our answer. And then again, we're going to multiply that by 2. So our number comes out to be 0.646 moles. 0.646 moles of bromine monochloride. And is it because I put something in wrong? Let's double check our answer. 25.8. And then we're going to divide by 79.90 times 2. Close that up. And then by 2. Oh, I must have put something in wrong when I did this. Okay, so this comes out to 0.323 moles of bromine monochloride. There we go. Scientific calculator issues. But it gives you an idea to see how the questions are worded and again, how we're going to run through them. And then for the following, we're going to do the exact same idea, but we're going to go from grams of A to moles of A to moles of B to grams of B when we finally run this guy here. So we're going to go 25.8 grams of chlorine gas, Cl2, times 1 mole of Cl2. And I already know this off the top of my head. It's 35.45 times 2 grams Cl2. Again, you can get that from the periodic table. Cross this out. And now we want to go to bromine monochloride, which is going to be this guy here, times 2 mole BrCl over 1 mole Cl2. That cancels out. And now we're going to multiply to get to grams. So now we're going to total up that bromine and chloride. So we have 79.90 plus 35.45 grams over 1 mole. That mole cancels out. And now we can go plug this into our calculator. And do some clearing real quick or erasing real quick so we can actually see what we're doing. 25.8 times 2 times 79.9 plus 35.45 equals this, all divided by 35.45 times 2. And we get 83.9. And again, because of this 5, we're going to round it to 84.0 grams of bromine monochloride. Submit our answer, and we're good to go. All right, now for gas pressures, what we're going to try to do here is we're going to just try to convert. So what happens here is that for 1 ATM, you have 760 millimeters of mercury. That's the unit for pressure. Also, it can also be 760 torr. That means the same thing. So what they do is they give us 736 millimeters of mercury, And now we're going to get it into ATM and we're going to get it into torr. First, let's do ATM, because for torr, it literally means the exact same thing. So we have 736 torr. But for ATM, what we now know is that for 1 ATM, we have 760 millimeters of mercury. This will cancel out. And now again, we can go to our calculator. 736 divided by 760. Take this out to 3 significant figures. We have 9.68. That should not be right. Yep, 9.68. And I messed something up. This is not correct. It should be 736 divided by 760. There we go. 9.968 ATM. Submit our answer, and we're good to go. Again, same thing here. We're just going to do some calculations. So they give us the equivalent, and we'll say that we have 29.2 PSI. And again, we want to get to ATM first. So 1 ATM on the top, 14.7 PSI on the bottom. And now we can go to our calculator, do 29.2 divided by 14.7. And we get 1.99 ATM. And then same thing, we're going to start off with 29.2 PSI times 760 millimeters of mercury. And we're going to have to do a little extra work. So, because we won't be able to do this quite the same way. What we can do here is, because now we have our answer in ATM. I'll take it to the easy way. Now what we'll do is 1.99 ATM times 760 millimeters of mercury over 1 ATM. ATMs cancel out. And sorry if you guys can hear my little guys in the background. I'll have to take care of them here in just a minute. All right, we're going to get this 1509.6. And again, we want to take this to 3 significant figures. So we're actually going to count this as 1510. That way we have 3 significant figures, but we've also done our rounding appropriately. Submit our answer, and we're good to go. All right, last question is the combined gas law. And as you can see, the combined gas law has lots of different equations set with it. So what it's going to end up looking like is this very long equation that looks like this. Oop, wrong thing that I hit. P1 V1 over T1 equals P2 V2 over T2. So we're going to be solving for either pressure, volume, or temperature when we're looking for these pieces. And so when we go here, we're going to answer some questions. Now, I will say, with this being said, we're going to want to make sure that we think about temperature, and usually we're going to use temperature in terms of Kelvin to make life a little bit easier, because otherwise this, well, it may not work out the way that we're supposed to. But in this circumstance here, because our temperature is constant, we actually don't have to worry about temperature in this situation here. We're only going to be worrying about P1 V1 equals P2 V2, because temperature is constant. When temperature is constant, this is called Boyle's law. So we don't care about temperature here. We only care about pressure, and we only care about our volume. So reading this guy here, it says a sample of neon gas at a pressure of 911 torr and a temperature that again is constant occupies a space of 632 mLs. So P1 is 911 torr, volume is 632 mL equals, and it wants us to know if the gas is compressed at a constant temperature and the pressure, now we'll take this out of our the scientific notation, and it'll be 1220 torr. What's the volume that we're looking at here? So what we're going to do is we're going to solve for V2. So we're going to take 911 divided by, or multiply by 632, and we're going to divide it by this 1220. The torrs are going to cancel out, and now our answer should be in milliliters. So we're going to do 911 times 632, and we're going to divide it by 1220. And we're going to get three significant figures, so this will be 472 milliliters. Submit our answer, and we're good to go. All right, I hope this helps you guys out a little bit to understand what we're doing for the problem. If you have any questions or concerns, feel free to ask. If not, have a wonderful day. Bye, guys.